All right, today let's look at implicit analysis inside LS-Dyna and how to troubleshoot it. If you've ever done implicit problems, the biggest headache is sometimes the model just doesn't solve because it failed to converge. So let's look at how to do some basic troubleshooting. What I've done today is I've summarized some of the key things that we should do for implicit analysis that you should do for every single one. We'll look at some example of the common ways an implicit analysis can fail. What I've also done is create an example like this. This material is made of rubber. This is a sort of a steel rod is going to move it, but that's actually a very difficult problem to get convergence, or rather, I should say, it's going to be harder to get convergence on. We'll look at some example of the key files that we can use to basically track and troubleshoot. And then we'll look at some basic troubleshooting steps. This video is by no means comprehensive, simply because I can't come up with enough examples to cover all the potential troubleshooting steps. It is very difficult to even envision what those will look like just me sitting in front of my computer. Like I think you do real projects, you run into them. Otherwise you don't, right? This is why like experience come from actually doing a lot of different things because you run into difficulties that you will otherwise not encounter. This is why, simulation is actually a hard practical experience that you have to gain as much as the theoretical knowledge. Okay, so let's look at some of the basic troubleshooting steps. Now, before I start, I want to sort of introduce this problem, this quick example model. So in this model, what I did was I created a rubber material. This is a hyperelastic rubber material that I'm basically using for this piece. This thing has a cyclic region attached to it, mostly because it's a sector. And then I have a contact which I created between these two bodies. There's different version of this contact pair that I've used. And then I have this thing mesh, pretty simple, right? Just 2 to 3 element across that thickness, and then all I have the rest of it is basically it fixed on this end, and then I'm going to apply the velocity. This velocity is like a trapezoid velocity that's just gonna push this part down, and then I have my implicit control template, control implicit template that I'm using to do the implicit analysis. Obviously, the problem is going to have a termination time of 1 second. There is no database card being written out. There is no control card being written out. Okay, that's a basic overview of what this example problem is. I also have the same problem on the ANSYS mechanical side. So you can sort of see this is what actually happens if it's solved correctly, right? I have this thing on the mechanical side, but I also create a different scenario in which it wasn't solved correctly by intentionally. For example, in this case, I have this thing moving in this direction, right? But I can also force it to move in the x direction more, like going down this way to see if it's going to create convergence problems, which is sort of what I did with the velocity profile. Is I have the velocity profile going this way. Okay, then I'm going to look at a different look at the rest of the topic is going to be based on this example problem. Now, if you think about why is this a good example problem for troubleshooting implicit analysis, this is a rubber material, so it's highly nonlinear. We have contact, and then also we have a large rotation that happens due to the way this arm is going to deflect downward, right? So if you look at the actual example here, this is clearly a large rotation problem. So it's going to have all three types of nonlinearity in the model, and we want to be able to sort of get convergence on something like this. It starts out also with an edge to surface contact, also pretty much a pain in the butt that have to troubleshoot a little bit to get it right. So there's a lot of different tricks you can use to get convergence on something like this, and there are right way to do it, there are wrong way to do it. And what I like to do in this video is to summarize this example. Okay. All right. In LS-Dyna, the first thing that I think every single implicit problem should do is to include these three different things, right? So I have my implicit control templates right here. This is my control template that has been updated to include the troubleshooting stuff that I generated today, right? So I'll introduce these things to everyone in this video. Okay. So first thing I think we should do is to set this parameter right here. This parameter, once you turn it on to some number, right, which is if you look at this parameter right here, the D3 ITE right here is going to set to every 10 iterations. Basically, for every 10 time step, not iterate time steps, every 10 time step in the implicit analysis, it's going to write into well, I'm sorry, for all 10 steps in the implicit analysis, the D3 iter database is going to be written out. So, and then every 10 is gonna reset. So basically, it's gonna write 10 at a time and 10 at a time, and then it's gonna reset it after every 10 time steps. So what you essentially have is by setting this number to some number greater than 0, right, is that you're gonna have a database file that let you basically do what ANSYS Mechanical let you to do, which is to check the residuals for where you have potential convergence problems, which is one of the most useful thing you want to have. So this right here is the equivalent of the ANSYS Mechanical version of the Newton-Raphson residual, right? So if you look at the Newton-Raphson residual right here, right there, that's something that as I will demonstrate in a second, that Dyna can also do with this iter database that you had to generate by setting this parameter correctly. The second thing we want to do is to set the RESPLT parameter here. What this parameter does is that it's going to output basically the residual forces into the iteration, the D3 iteration file, D3 iter file, right? So without this, you won't be able to see the residual force like you can see with the ANSYS Mechanical. So both this parameter and this parameter has to be included. So this is basically a given, right? So what I've done in the data in the template that I have is I've set the RESPLT parameter in the extend binary, right? And then also I've set the D3 iteration parameter inside the conjoined implicit solution. So by having these two things included in your template, or in my template in this case, I will be able to do what ANSYS Mechanical does, which is the primary goal I have, right? And then lastly, also that if you were to set NL print to 3, it gives you a lot more information in the D3 HSP and D3 message file. And then if you set the min info here to 1, you also get more contact information in terms of penetration for each of the interfaces. So these are obviously all things I think we should just include in each of the implicit analysis, because by having these, it gives you a general way to troubleshoot all implicit Dyna models, right? So that's the basic thing I think we should include for all of the implicit analysis. Even if you don't need it, even if the convergence is easy, we should still include it because it's very good when it doesn't work and you can just check it, right? That's why it's part of the template. Okay. All right. So with these three things mentioned, right, which I've essentially built into my template here. One other thing that we should do, we should look at right now, is look at all the ways in which an implicit analysis can fail to converge. And this can be so many different things. I think the way I can best summarize it is with these sort of bullet points that I can think about. And there are a lot of these things are, it's not like they're just by itself it's causing convergence problems. I think they're all contributing to it, right? Some of them is going to break the model right away. Some of them is going to be a sort of just making the model more difficult to converge. So the first three are basically just related to some kind of rigid body motions, or you have unconstrained model, the model of not being constrained properly. With these three things, there are several different ways in which we can handle it, right? So I'll talk about that in a second. Of course, the three types of non-linearity all contribute to it. Now, it doesn't mean you can't work with implicit analysis when these three are present. In the contrary, you can, right? And that's just what makes it more difficult. So you have to check for each of these things, right? Check your material model, check your contact, and these are the things you have to essentially look at. Now you can potentially have large element distortion. That's usually a function of element quality at the start. So your mesh quality becomes a lot more important in an implicit analysis because a poor element quality can also cause convergence problems. In addition, many other things that can happen. Inside the explicit, right, it could slow down your job by reducing your stable time increment. And that's a different type of problem for a poor element quality. Of course, that's also related to accuracy, which you want to double check. Okay. Now the implicit control settings, we have various default settings that I've generated in my template. One of the reasons to have a template is so that I can play around with numbers and very quickly adjust the behavior of the model in terms of convergence. But this is obviously a key things. And of course, mesh quality, like I said earlier, is also going to be important, which is related to element distortions. But element distortion can also be a function of the loads of the support of also material nonlinearities. So a lot of these things are interconnected, right? So I named these 9 things just to sort of outline for myself all the things I have to consider when I'm trying to get a difficult problem to solve implicitly. And sometimes it is worthwhile to do so for a lot of different reasons. You want a model to solve implicitly. You cannot do it explicitly. Okay. All right, so let's look at a couple different key files that we want to sort of troubleshoot with. Okay, so this is a very good flowchart that I got, I think, from the documentation or from the implicit guide. But basically, the way troubleshooting works inside LS-Dyna, right, is you're gonna have to generate these files, right? So D3 HSP usually is generated. We'll look at how to use it in a second. This one is generated as part of the error message, so you can control the detail that's in here. These two are fine, right? The D3 iter file is the most important one in my opinion because that allows you to visualize where the convergence happened. It's like a mechanical with the Newton reference and residuals. You are able to pinpoint the problems and go to that region of the model and fix things. Okay, so this is the most important part. And the other three are just the basic message that happened when the job finishes, right? So it's not that important. So we'll look at some of these examples. So here is a visual of the D3 iter file, right? So over here, basically, so what we do here, so let me just show you real quick. So I can show the example that I already made. So if I go to open and go to binary plot, I can say, for example, I can go to my very first one, implicit trouble. I'm gonna use this one, and then I can just click on D3 iter right there. This D3 iter file is generated look like this, right? And then I can basically open up here and go to NVD and go all the way down to residual force. If that's a residual moment, there's a residual force. And if I look at residual force, you can sort of see right there. In this specific model, my convergence problem happened due to the contact between here and here, right? And the resolution could be simply I need to change the contact setting or I need to move the bar a little bit slower. But you can sort of see this is exactly the same thing as you will see inside ANSYS Mechanical if you're familiar with the product, which is that you get to see this type of problem right here. You see that? It's exactly the same type of information that you're getting from here. And that tells you that this is a very good way to troubleshoot, right? So this tells me my problem for convergence here is due to that contact pair. Okay, now because of that, we can also look at other things, for example, right? So this is a good way. Another thing for troubleshooting inside LS-Dyna is to use the D3HSP view function here. So over here, what I would do is that I would just take it to the right folder, which in this case, this is the right folder, and I'll just do load. And once I load this, it's gonna generate a ton of information here. Right, so for example, I can look at, well, I'm not going to go through all of these, obviously. So you can sort of look at all of these things that can give you some basic information about what's happening, right? I can look at the text file here. This is not very easy to see, but one other way you can do this is that, for example, I can just check displacement norm, which is my convergence for displacement, and then I can plot it, and that's going to generate a plot that lets me see how the displacement norm is changing over time. Okay, and this is as a function of iteration steps, and then so on and so forth, right? So it's a pretty good way. And then over here, obviously, this file is not just for implicit analysis. A lot of the useful information for the model is located here, right? But this one doesn't definitely have the implicit statistics. That's going to be very useful, and then you can also plot these things, which give you a sense that this is a very similar to the type of functionality you get in mechanical, where you can sort of trace, say, for example, force convergence, right? This kind of stuff you can see in mechanical pretty easily. In Dyna, it's going to take a little bit more effort, but you can definitely do that within the D3 HSP file, which gives you that information that you're looking for. Okay. All right, that's the second thing. These are the most common ones that you can sort of look at. I think for every implicit problem, we want to get into looking at it this way. It's going to be very, very useful. And now some other common troubleshooting steps is that one other thing you can do is use control implicit dynamics to reduce rigid body motion. So we talk about one of the many common ways the problem can fail is to having these rigid body motion or under constraint models, right? And when that's the case, you can actually allow some rigid body motion to be present by setting the control implicit dynamics. And that's happened here basically with this portion of the keyword template. This right here is going to give you the parameter you need to set that initial dynamics. So usually you set this to 0.6 and this to 0.38. That's a pretty decent way to do that. Okay. And then what you can also do is do inertia relief. Now there's something you have to be very careful about. So I want to show you what happens. So right here, I set inertia relief to essentially ignore the first 10 modes. This is going to be very, very wrong. but you can sort of see it gives this kind of response in the model, right? You can sort of see this is clearly not correct. What you would expect should be something that look like this, right? You should be pushing this whole thing down. But because we're ignoring this mode of deformations in the dynamic analysis, right, it's doing something really, really weird. So this is clearly not correct. So when you do want to use inertial relief, you have to be very careful with how many modes you are removing and for what reasons, right? But this is one way you can do it, is to remove those rigid body modes from the model by using inertial relief. So for the template I have, I'm going to comment this out until I have a very good reason to use it. Okay, and then I have the parameter set at 202. So it's going to remove the first two modes. I can also set as a frequency. The thresh is a frequency that I can essentially set, which is also pretty useful. Okay, but implicit dynamics should be turned down in the beginning. That would really help with the problem. But if you turn it off, you can also consider using maybe inertial relief with only the first mode, so you remove any kind of rigid body modes from the model. All right. All right. For contact, implicit analysis is really much better handled with the mortar contact. I can do a quick demonstration here. With a mortar contact, what you sort of get is something that looks like this, right? So for example, this is the mortar contact. This is the This is the one with the mortar contact, and this is the one with the bar going this way. You can sort of see there's some really weird things. And it's doing that. So you can sort of imagine you can even get this thing to converge by doing some kind of model that look like this. On this side, it does something a little bit similar, but in this case, I don't have any inertial relief, so you can still get this thing to work. But you can sort of see the deformation is slightly different. So you see this mode right here has that little going upwards mode because I use inertial relief to kill some of the initial modes. In this case, I don't have any initial mode, so you actually get the correct responses. You do not want to use inertial relief. That's the key point, right? You want to use it, you have to be very, very careful. For this problem, it's certainly not applicable, which is one thing I have to sort of demonstrate. I'm hoping I'm demonstrating right now, right? But this kind of contact is way better for convergence behavior than a basic automatic contact. Like this is right here is an automatic contact. You can see I'm not even getting any convergence because it couldn't resolve this contact right here. You just could not resolve it, right? And that's why a mortar contact does a much better. This is right here is with a mortar contact. It does a much better job of that, right? We don't want to use VDC, so set that to 0. We can also adjust the penalty stiffness, which is the SFA parameter of the contact pair. So in this case, it's inside mechanical. You can go here and you can change this SFA parameter right here. That might have some effect that you can sort of play with to see if you can get a convergence to work. Okay, and that's really overall what it is that the mortar contact is a very good contact to use for implicit analysis. And then we can also managing initial penetrations, right, with the control contact or with the ignore parameter in option card 3 of the contact cards. So this exists everywhere. I usually just leave it alone, leave it to default, but you can certainly change them if you need to. Okay, you have to modify the contact card to do so. And lastly, of course, the arc length and the line search exist to help with the convergence, right? But you want to use them very carefully. In my opinion, like I personally feel like I want to start a model with those two lines disabled. Right, this sort of accounts for the arc length. This one accounts for the line search parameters. I kind of want to disable them to look at how the model behaved. Then I will turn them on selectively and carefully. Arc length searches for the convergence behavior curves, and then line search will basically allow you to try to find an optimal time step, right? So together, they give you a better convergence behavior because it will find the minimum amount of time step it takes to get convergence, right? It's great when it works. Inside mechanical, it seems to work really well, but inside LS-Dyna with the default parameter, it doesn't always work very well. For a lot of problem, you want to sort of don't use them unless you have looked into exactly what the problem is and why it's helping you. And also, control implicit dynamics does not work with arc length methods, right? This is for a quasi-static problem only. So one of my past mistakes that I've made was I actually had the control implicit dynamics and arc length method enabled at the same time. So what I really should be doing is to disable both of these lines, leave control dynamics at the start, right? So I don't use them at the same time. If I use them at the same time, it's not essentially doesn't work. And that's one thing to pay attention to, right? Something you want to disable. And lastly, you know, ANSYS and LSCC and Dynamo, they've created some really good documentation for how to troubleshoot, right? So definitely want to give them credit. I learned from them as well, right? So you'll see this is right here. This first site is for some basic information for troubleshooting. These are all pretty generic, right? I don't think they are intended for one specific type problems, but it gives you an idea of what you want to look at, what you want to do to get to look for convergence. The second place is in the volume one, the appendix P of the documentation. There's a troubleshoot for convergence section. Read through them. I've summarized some of this in my slides as well. I learned from it, right? Lastly is with the control, the implicit guide that's published by Dynamo. Now it's part of ANSYS. This guy right here, if you scroll down right here, you have a section 13 called for troubleshooting for convergence problem. This is very similar to this and very similar to this. I think they are all come from the same place, really. There's a lot of very similar things in here, but it does give you some idea of what to look for, right? So one awesome thing about D3 HSP is that, say for example, if I want to go here and I want to look at a D3 HSP view and I want to load it to one of the model that this solve, right? Let's say for example, if I go to here, I select folder, then I do load. And then what you can sort of see is that you get these convergence curves that you can sort of visualize pretty well, and that's essentially what the model is showing. So it does a good. Oh, this is kind of slow. Sorry. So I'm not gonna wait for it. But basically, you can see the information that is displayed in some of these messages right here by looking at the D3 HSP viewers, which is a very good way to. This is actually it's a bigger file, so I guess it's not really loading. So we'll leave it alone for now. Okay. And then lastly is that I wrote down some section here. These settings, I mean, you can follow them. For me, I think having a template gives me the freedom to change what I want. For most of these, I do have very similar to what they have here, right? But for the most part, as soon as you have a code template like this, right, it becomes very easy to manipulate the behavior of your implicit solver. From one solve to another, you can parameterize all of these settings and run case files to check to see which one behaves better. So it becomes a very easy thing to manage once you have that. Okay. All right, that's the end of my video. This is by no means everything, but I think if you follow the basic guides for these three things, right, then you look at the file with the D3 HSP viewer and you look at your D3 iteration database file, you're gonna get a pretty good way to troubleshoot. This gives you as much power as you have inside ANSYS Mechanical, if not more. So you certainly should give you the way to get just as much convergence as you can get with ANSYS Mechanical. I always compare to ANSYS Mechanical because I do believe it has a very good implicit solver, right? Very convenient. And this gives me the power to do the same thing. All right, thank you.